Allow me to introduce the last speaker of the day. So that is Professor Roger Jaspers. And Roger is an associate professor here at the University of Eindhoven. He also is the head of the fusion group at Eindhoven University. And furthermore, he is the coordinator of the Master in Fusion at Eindhoven University, which is one of the two largest European masters dedicated to fusion. So we're really happy to have you here, Roger. And yeah, maybe to mention something that Roger was one of the founding fathers of FusionNet back in, I was even before 2010. So we're happy to have you here. Thank you for joining us and also for being active in FusionNet and addressing the students. So Roger, welcome and the floor is yours.
Thank you, Dario, for this nice introduction. But let me first see if I manage to share my screen, because share. Yes. Okay. I assume it's visible right now?
Yes, it is.
It's very good. Okay, well, I didn't follow the complete program for today, but I assume if people talk about fusion, that 70–80% of what is being told to you today is about tokamaks, about ITER, about the fastest route to a fusion energy power plant. But I would like to address the alternatives to a tokamak. So this I do under the title Smarter Than ITER. You see there question marks. I guess that most of the participants, at least I hope you have heard of other confinement concepts, and I would like to discuss what are the prospects of those. So let me just see. You see nice pictures here of ITER. Everyone, I assume, has seen this. There is a large effort in the south of France for 15 years now. People are building it here. Looks great. I hope you all have the opportunity to go there once. It's so impressive to have it in there. But you also see it's big, it's expensive. It takes a long while to build it. So that allows me the question, can't we be smarter than doing it in this way? And also, if you just follow the news, I just took randomly some of the news items from, well, say, on Google you can find everything, but I tried to have some more decent literature in here. You see here the problems of ITER, a fading dream of fusion energy. A 5 years delay would spell the end of ITER. And this was published in 2014. By now we have 10 years delay, so you can imagine what that means. ITER, the world's most expensive scientific gamble. The Congress in the US divided over the future of the US ITER contribution, etc. So this doesn't sound very positive for our main project, our starring project. On the other hand, you read also just the opposite. Laser fusion extracts net energy. Oh, ITER cannot do it, but laser fusion apparently can do it. Or we can have cold fusion, or there are plans to go to the moon for mining helium-3, because you also can make fusion with helium-3. We're not considering that in ITER. And then you often find something like breakthroughs. US scientists make a crucial step. Or my favorite one, actually, a US team builds a nuclear fusion reactor, and that's garage. And I can tell you that is probably true. Actually, and Eindhoven will build that same fusion reactor. It's not so very difficult to make a reactor in which fusion reactions take place. So having seen this compared to my previous slide with all the problems of ITER, so can't we be smarter? And let me then highlight two more of these. One is an ignition first in a fusion reaction. So in 2021, there was a big fuss in the fusion community because at the National Ignition Facility in the US, they made a record shot in which they produced more energy in the fusion reaction that they inserted to start up this fusion reaction. And that's what we want, net energy production. Yeah? And that is not in a tokamak, it's not an ITER-like device. So should we reconsider ITER? And then something which is also we should take into discussion in the recent years, say the recent maybe 5 years or so, there is an increased interest of private investments into fusion. Yeah, so I have also here something: investors warm up to nuclear fusion promise of cheap power. The private sector investment increases, investments grow. Nuclear fusion has attracted 2 billion in venture capitalists and private funding, and this was 4 years ago. So if you add it up, you see here in this plot, which I took from the Fusion Industry Association, all the alternative fusion companies, private companies that have been established as a function of years, and you see that in the last 5-6 years there is an explosion of fusion, new fusion companies, and they're not all tokamaks. Some of them are, but most of them are not. And there are even several companies that attracted more than 200 million in investment. Can you imagine, for a technology which has not produced a single kilowatt hour on electricity, people are prepared to pour in millions because of the prospect it has. Now, before going to analyze all these different companies, I would like to spend, well, I don't know, hopefully less than 10 minutes. No, I think 5 minutes, just on giving you the basic fusion requirements before we start to analyze, these different concepts, because I think it's really crucial that you know what we're after before we can decide whether a concept is valid, yes or no. And it might be for, I'm not sure, this audience, I understand today is a bit mixed. There might be some bachelor students, some master students, some PhD students in the audience. So for some of you, this might be trivial, but for others, I think it's good to set the basics out. I think all of you probably know, if you do nuclear fusion, you try to bring two positively charged nuclei close together, and this costs energy. Yeah, so this is depicted in this is just the Coulomb barrier. So the energy you needed because of the repelling Coulomb force to bring two nuclei close enough together. And in this picture, if these nuclei come as close as what I indicated here by the distance d, which is typically of the order of 10 minus 15 meters, the nuclear distance, yeah, then the strong nuclear force sets in action. There's an attractive force, and this brings these nuclei together, and then energy is set free. For well, we all know how the Coulomb energy is made up: the charge of one particle times the charge of the other particle divided by the distance. Yeah, and if you put this distance 10 minus 15 meters, you see we need an energy of about 300 keV. Okay, so that sounds easy. We can accelerate particles to 300 keV. We can let them collide with each other, and we would have fusion. Yeah. The probability that you have fusion, this is depicted in this picture here. And here you see indeed that the picture that we had here to be in the range of a few keV, a few hundred keV. This value here is a bit shifted because of quantum mechanical effects. But you see, relate this cross-section to the probability that fusion takes place. What we learned from this picture is that dt, the red curve, the tritium, has the largest probability. It's about, well, not a complete order of magnitude, but at least a factor of 5 larger. The top value is a factor of 5 larger than any other fusion reactions. And the good thing is also that this peak in the cross-section is at a relative low energy compared to the others, like deuterium helium-3, proton boron, or whatever is in the picture. So I would say if we start a fusion reaction, probably the easiest one is to go to deuterium tritium. And then we all know that brings helium and a neutron as a reaction product. But you see also my title. My title says there are 3 reasons why fusion is impossible. The first was we need to put in a lot of energy. This was the Coulomb barrier. The second is that the probability for fusion is very small. So the cross-section is 10 minus 28 meters. that's related to the cross-section. But the main reason why it's impossible, fusion, is that if we accelerate particles to large enough energy, most of these particles do not fuse, but they lose energy because of interactions with other charged particles. So you easily can imagine if I have a head-on collision between one particle at rest and the other one accelerated to 300 keV, then they will come as close as this distance d and you have fusion. But most of the time, these particles, they miss each other. And if they miss each other, the other particle starts to move. So there is a transfer of energy, which means that the accelerated particles loses energy and the particle at rest gains energy. And if you now would calculate what is the cross-section, again, related to the probability that this takes place, you see that to make fusion, which is the green line, it's the same curve as I had in the previous plot, so then we gain energy, that this cross-section is always, for every energy, lower than the loss of energy due to these collisions. So the particles that miss each other. That is represented by this red curve here. And you see that even where the cross-section for fusion is maximum, there is at least an order of magnitude difference between the loss of energy and the gain of energy for fusion. So we never can make a positive energy balance if this would it. And that is why I put it as a title, why fusion is impossible. Yeah. Unless, however, we confine the energy. So if this particle, which we have accelerated to whatever, 300 keV or so, loses its energy to other particles, if these particles would leave the system, then we're lost. But if we could make sure that the energy which is transferred to the other particles, if this stays into the system, then also the other particles can take part in a fusion reaction. And this is what we are after. So I think number one, to check if you want to see if a fusion concept is valid, could work as an energy source, number one is to check if there is confinement of the energy. And there are different ways to confine energy. I mean, the sun confines the energy, just make sure not all particles escape by gravitation. In a tokamak, we try to keep the particles together in the system by applying magnetic fields. And as we later will see, with laser fusion, we just use inertia to confine the particles. Yeah? And that all leads to very different reactor sizes. Yeah? So this is number one. Confinement is needed. Then number two, where I need a very short derivation, I think a fusion reactor, whatever it is, I put here as a picture a tokamak, the ITER tokamak, but what I'm going to discuss now is device independent. I think a fusion reactor would work if the power from fusion, which we have here, would be bigger than the power we put into the system to heat up the plasma, to accelerate the particles to sufficient high energy. Now we can just use this equation and see what is the power of fusion. Now I'm not going to explain this in full detail. For some of you, this might be already known, but for others, I think I just make it plausible that the power of fusion is just taking care of how many reactions take place within a second. And this is related to the number of deuterium particles, so the density of deuterium, times the density of tritium, because they collide with each other, times this factor here is the cross-section times the velocity. So this is related to the probability a fusion reaction takes place. And this is the energy which is set free in a fusion reaction. That should be bigger than the power we put in. Now I can tell you we do not know exactly how much power we need to put in, but in steady state, the amount of power you put in should be the same as the amount of power the reactor loses of what you've put in. Yeah, and the amount of power you lose is given by the total energy in the system divided by a parameter called the energy confinement time, tau e. Here I don't know what it is, but just the time scale on which you lose your energy. Accepting this, and using that the density of deuterium and tritium is the same, and that the energy content is given by the density times the temperature, with a factor of 3/2, which comes about by thermodynamics. This then arrives, if you would fill it in, to a criterion by which this first line is satisfied. And I can write that criterion like I have here. Density times the energy confinement time should be bigger than something. But I can also multiply both sides with the temperature, Kt, the Boltzmann constant times the temperature, and then we arrive at this equation. Now, this equation is what I have on top. That's the only parameter I want to discuss with you. Because that means that a fusion reactor works when we fulfill this, what we call triple product. So the product of density, temperature, energy, confinement time should be bigger than something. Yeah, that's something. So the right-hand side, this is what I plot in this plot in the picture below. So the red line is just giving me temperature squared times this constant over the cross-section. Yeah, and I can plot this as a function of the temperature. So that means that it is most easy to run a reactor at the bottom of this plot. So if you're always above this red line, the reactor will work. And you see this curve has a minimum at 15 keV. So that's why we normally say a fusion works best at 15 keV. You can go to higher or lower temperature, but then the reactor is not running in an optimal state, so it's more difficult to run, but it's still possible. You also see that you can exchange density, temperature, energy confinement time. Yeah, so now we might want to keep the temperature around 15 keV, but we could go to a high density, a low energy confinement time, or low density, high energy confinement time. And that is just the two extremes we have. The low density, high energy confinement time is magnetic fusion, whereas the opposite side, high density, low energy confinement time is what we call later on inertial confinement. But everything in between is also well possible to have that. Yeah? And this is that same plot, the triple product on the y scale, the temperature on the x-axis, and here you see where all the present or all the past experiments, I must say, how they performed in this curve. And the ignition, so the Q is 1, the break-even point, what we were just discussing this line. So the red line on the previous plot is the same as here, the middle red or orange line. You see that ITER at least should have parameters above this line, so it should produce net power. Yeah. Now with ITER, if I go back, well, first you see, is there no further progress? Well, to go to a higher triple product, if you stick to the tokamak line, the only way you could do is go to bigger devices. And that is what ITER does. So it's not that we don't make any progress, but only because it takes a long time to build a big machine like that. Now, so far so good, but ITER takes a very long time. And the reason for this, there are many reasons. I will not go to all the political reasons for that delay, but you could also phrase it like ITER is a very complicated machine for several reasons, but from the technological point of view, the main reason that ITER is so complicated has to do with the fact that the fuel is deuterium tritium, and we don't have any tritium on Earth, at least not enough to run a reactor for more than half a year. So we have to breed the tritium itself. And the second reason is the reaction produces neutrons. And if it produces neutrons, you have to shield it against. Yeah, not all materials can withstand the neutrons, just not even the magnetic coils by which we confine the plasma, as we just heard from Susie Speller. Yeah. So consideration number one would be, can't we simply make a reactor without the deuterium-tritium reaction producing neutrons?
Roger, you are still in slide 17. Is that okay?
That's okay, yes.
Okay, just make sure. Yeah.
No, I was trying to introduce slide 18. Yeah.
Sorry about that.
Slide 18, as you see, answers this question. Can't we use an anetronic fuel? So in my opening slide, I showed you there are plans to, for instance, go to the moon to mine helium-3, because with helium-3, there is a fusion reaction possible. So as you see here, helium-3 plus deuterium gives me helium-4 plus a proton, no neutrons. Yeah, so that would be an ideal reactor, no shielding needed. We can make it smaller, no safety issues. Another alternative would be, this is this orange line here, proton per boron 11. Also in that case, we just produce charged particles. Charged particles are easy to decelerate, to transfer the energy to it, and no issues with neutrons. And that is what people always, or several new companies propose. Let's get rid of the deuterium-tritium reaction. Whereas the main reason for the deuterium-tritium was the higher cross-section. But this cross-section, as these people claim, is just a factor of 5 lower. So you could say, hey, well, if we just have a factor of 5 less fusion power, but have a much easier and cheaper machine, maybe it still has advantages. However, in this respect, I think that reasoning is not fully correct. Yeah. Because the cross-section is a factor of 5 lower, as you see here, but you also see that this cross-section has its maximum, in the case of the green light, at a 5 times higher energy than in the case of the deuterium-tritium. So you need a 5 times higher temperature to reach the maximum cross-section. Now, you should realize that if you have a reactor, there is always a pressure limit. Yeah, you try to make the reactor so hot to reach sufficient fusion temperatures, and then you put in as many particles as you want, and the number of particles times the temperature is the pressure. Yeah, so if you run, say, the ITER tokamak, you do this at the maximum density at the optimal temperature. Now, if your temperature goes a factor of 5 higher, it means your density must automatically be a factor of 5 lower. Then you still have the same pressure in the machine, and you cannot overcome this pressure. But if your density is a factor of 5 lower, it means the fusion power, which goes with the density squared times the cross-section, is then a factor of 125 lower. Taking this into account, my conclusion at least is that a neutronic fuel, doing it without deuterium-tritium, is possible on paper, so it's not that it's not possible, but you get 100 times less energy out of the reactor than you have in. And since we already have at this moment very low, we have to work very hard to get a positive outcome for the deuterium-tritium reaction at all, I think looking to aneutronic fuel is very unrealistic as a first step. Yeah, so concepts with this are very difficult to realize. They're not fundamentally impossible, but I cannot imagine that the first fusion power plant will be like this. So no need to go to the moon, I would say. But this then brings me to another small problem. That means that we have to live with the deuterium-tritium reaction. And I guess it must be known for you, there is no tritium, so we have to breed the tritium in the reactor itself. We do this by the neutron which we produce in a fusion reaction will need to react with lithium, which we store on a wall. But here you see for the ITER reactor, just the tritium factory. So we have to get this tritium out of the machine, yeah, and reprocess and put it back in the machine. And I have this picture here because you see the tokamak building, the ITER device itself is 57 meters high, whereas the tritium factory itself is already at least a similar size, if not bigger in volume than the tokamak. So even if you would be able to make a very tiny tokamak, which is not possible anyhow, but assume you would be able, you still need a factory of this kind next to it. So I would say, as an intermediate summary here, to check first on a fusion concept, you need that you know confinement and that you need to fulfill this triple product criterion. Concluding from those two is that the deuterium fusion reaction is easiest and the optimal temperature is 15 keV. But as a consequence of the deuterium-tritium, we need to do the tritium breeding and we have to live with the neutrons. So the tritium breeding means that the device will be very big and complex, as I just showed on the last slide, And the fact that you produce neutrons means that it is a nuclear facility. So you have to fulfill all the licensing and safety requirements that are met for nuclear devices. So it's not, even if you have a simple concept, it will be cumbersome to build it. Now let's see what alternatives people have come up with compared to the tokamak. So before doing that, one more slide on the tokamak. We need confinement. How is this done? In the tokamak principle, I guess you know it. So the principle is here, we need to heat the plasma to this temperature of 15 keV. If you would do this in a linear reactor, it would mean particles move randomly across and they will hit the walls and then can never reach the required high temperature. So you must act to prevent that particles hit the wall. And you can do this by magnetic field simply because charged particles gyrate around the magnetic field. And in this way, their perpendicular motion is strongly reduced and they will not leave the system in the perpendicular direction. Of course, they will leave the system in a parallel direction, parallel to the magnetic field, but you can solve this by simply making these magnetic fields going around in a circle. That is the basic 30-second explanation of a tokamak. Now, well, this then leads to these big events, but there's no need that you do the confinement by magnetic fields. There are, let's have a look to concepts that do not require magnetic field and are proven to work. Yeah, you might remember my slide number 3 or so said, okay, in 2021, in the US, net energy was extracted in a fusion reaction. That was laser fusion. For those of you not fully aware of laser fusion, I mean, the principle is depicted in these 4 pictures here. You take now not a plasma, not a hot gas of deuterium tritium, but a pellet, a solid state pellet of deuterium tritium ice, which is this blue part here. If you would irradiate this pellet extremely homogeneous from all sides, put a lot of power on this, and this you can do with lasers, as you see in the picture here. What happens is that the outer shell heats up. If it heats up, then particles will escape. Yeah, they evaporate. But, well, if something, you have this, what is it, law of Newton, action equals reaction. If some parts go one way, then there will also be particles that go the opposite way. And in this way, you can compress part of your fuel. And if you compress it, your density will increase. And if you do this fast enough, if this goes adiabatically, also your temperature will increase. And then we might come to a position where this triple product, density times temperature times energy confinement time, is fulfilled. And be aware that the confinement time here is just the size of this pellet divided by the velocity of these particles with which they move. What is their kinetic energy? So this confinement time is, this pellet is 1 millimeter or so, the velocity 10 to the power 6. So this confinement time is very, very short, of the order of a nanosecond, but your density is way higher than in the tokamak. It's an order of, it's about 9 orders of magnitude larger. So overall, the product of both is still in the same ballpark. Yeah. So here, adiabatic compression leads to the required conditions, and you can have fusion reactions. Now this has worked, but let's look to the numbers. No, before we look to the numbers, you look to the pictures first. First, even if you would claim it's smarter than ITER, it's not smaller than ITER. Yeah. So this is this reaction chamber. I think it's 12 meters high, just to cover this 1 millimeter pellet in here. This is the power building of the power supply for the lasers that are there to compress this pellet. Yeah. Inside this reaction chamber, you see the crane and the beamer, on which in the center of this beamer you have this hole room, and inside this hole room in which you shoot these lasers, we have this tiny pellet. So it's very big, I would say. But now to see how we should interpret the results of that, Well, first, I want to say it was a great achievement that this lab was able, by absorbing 2 megajoule of laser power to this target, to this pellet, reaching out 3 megajoule of fusion power. So you see, we have increased the energy by a factor 1.5, a great achievement. However, taking into account the low efficiency of the laser, to have 2 megajoule of laser power absorbed by the pellet, we need to extract from the grid like 400 megajoule. All the rest is lost by the efficiency of the laser or by the laser path and the absorption by the pellet. Now you also could say the opposite side. If you produce 3 megajoule of fusion energy, this is thermal energy. If you convert thermal energy into electricity, you lose a factor of 2/3 about. So probably you cannot make more than 1 megajoule of electricity out of that. And now it gets a bit less, looking less positive, yeah? So you took 400 megajoule from the grid and you are back to have 1 megajoule of electricity. So to say that the laser fusion is close to a power plant, I cannot support that statement. Yeah. Moreover, there are other things. Yeah. So, for instance, if you would say we have produced 1 kilowatt hour on electricity, well, I think the current market price for this is a few cents of this. But to make this pellet is about $10,000 because it has to be extremely homogeneous. It has to be made of deuterium tritium, whereas tritium is very rare and expensive to work with. So before this really comes to a reactor concept, you need to reduce the pellet cost from $10,000 down to 10 cents or so to make a net profit. Moreover, at this moment, this lab can do about 1 experiment per week. Whereas if we want a 1 gigawatt power plant, we need to do this 10 times per second. So also these are 5 orders of magnitude. So my conclusion to this is, at this stage, this laser fusion concept is by far not closer to a power plant than the tokamak type is. Yeah. Okay, let's skip that slide. Of course, there are still people working into this field with also clever ideas. So one way I want to highlight here is you can have this compression of this pellet also in a different way, not using lasers, but as the UK company First Light Fusion call it, the big friendly gun. Their concept is that they accelerate a metal plate, this metal disc, which is you see here in the copper colored, yeah, shoot this onto a cube. Inside this cube, we have the deuterium tritium pellet, but they have arranged the material of this cube such that a shock wave will form around the pellet, and the shock wave compresses the pellet to the required densities. Also, this is a form of inertial energy, and the big advantage compared to laser fusion is that this, what they call big friendly gun, has a much higher efficiency than laser. So it can put whatever from all the used power, about 50% in accelerating the kinetic energy of this metal plate. Yeah. So there are ways to go around, but still also here you're far away from a reactor. Okay, a few more concepts. I think in view of time, I might speed up a bit. Yeah, there are people that have tried to confine the charged particles not by magnetic field, but by electric field, much easier to work with. Then you come to what is called a fusor, and a fusor works like this. You have a high potential in the center. If you have an ion at the outside of the reactor, the ion will be accelerated towards the center, the negatively charged center, gains kinetic energy. If the potential difference between the anode and the cathode is about 100 kilovolts, the ion will arrive at the center with a kinetic energy of 100 kilovolts, passes through the center, gets decelerated afterwards, comes here and returns. So in the end, the ion motion will be an oscillation in here. But if ions come from this side, they oscillate in this way, and then there is always a possibility that the 2 ions fuse in the center. This works. This produces fusion reactions. However, this is never leading to net positive energy, because the electrons, they go the opposite way, they hit the wall, and all the kinetic energy of these electrons are lost. And you can calculate back of the envelope that this system will never lead to positive energy because the losses are always bigger than the fusion reactions in this case. However, fusion reactions will occur. There are ions that are colliding with each other and making fusion reactions, so you can produce fusion neutrons in this. And this is exactly the concept on my first slide where I said a US team builds a fusion reactor. This is what you easily can build yourself. But there are companies that build this as a neutron source. And neutrons you can use also whatever to make medical isotopes or whatever. Here is just one of these companies that makes a lot of profit using this concept, but not for energy production, but for medical isotope production. Yeah. Then on an alternative scheme, you could say, why not combine fusion with fission? So you might recall the numbers. In a fusion reaction, each neutron, so in each fusion reaction, 17.6 MeV on energy is set free, and one neutron. Of course, a neutron has 14 MeV, but I mean, a fusion reaction delivers 17 MeV. In a fission reaction, however, there is 200 MeV energy set free per neutron. So if you would use the fusion neutron not to slow it down and have the 14 MeV kinetic energy transferred into heat, but use this neutron to trigger a fission reactions, you can multiply the total amount of energy by a factor of 15 or so. Which means that if we have a fusion reactor which is not yet at break even, just like a reactor like JET, which had a Q of about 0.5, if you would cover the wall of JET with a fissionable material, you could still make net positive energy. And whether this would be a reactor or a laser fusion device, it could work always, putting this fissile material in the reactor walls. And it has several advantages compared to a fission reactor, simply because it's not a chain reaction. You can also use natural uranium. No enriched uranium is necessary because with the fast fusion neutrons, also 238 uranium is fissile, and you produce much less waste. Now, all this sounds very positive. However, my personal opinion about this is that, well, you also complicate the fusion reactor much more because you have now much more stringent safety requirements on this concept. So whether the more complication of the how to say it, whether the advantages of having more energy outweighs the more complicated machine, I'm not so sure about that. Yeah, but still, several companies, but also several governments are working on this. Here you see Russia and China, both are looking into this direction. Yeah. Now, I told you to make a fusion reactor, we need to fulfill this triple product. We went to two opposite ones, low density, high energy confinement. That's what I would say the ITER, the tokamak line. And you have the other extreme, high density, low energy confinement, laser fusion or initial fusion. But no one prevents you to be in between there. And that is what we call magnetized target fusion. And there are at least a handful of big players in the private investment companies that focus on this because they say, well, if you do not want to go to the extremely high energy confinement time, we can do with much cheaper magnets. We do not need these big superconducting magnets. We also can reduce the cost on this. On the other hand, if you don't go to the very high densities, we do not need that powerful lasers. We also can compress the pellet by not just a factor of 20, but just a factor of 5 might be enough to do that. Yeah, and then we can reduce on the energy needed for compressing this pellet. And one of these companies is General Fusion. So their concept is more or less depicted in here. At the top, they make a small plasma with a very modest temperature and density. They inject it into this vessel. Then you see all these pistons here. In this vessel, we have a rotating liquid, a heavy metal liquid. With the pistons, you compress this liquid. And if you compress it and the plasma is inside, you also compress the plasma. And if you compress this plasma, the plasma will heat up adiabatically. And then you might also, in this case, reach the required temperature. On paper, this looks great. The pictures also look very nice. However, there are some big hurdles to overcome for this company, because you can compress and increase the density only by the shock wave to the required density and temperature if this plasma is very homogeneous. Yeah, only when you have perfect symmetry you can really compress it. And up to now, it looks like there are many instabilities occurring before you have reached the required density. So the results yet are not in any way close to what is the triple product that is required. On the other hand, this company is progressing and they make progress, so they are still a large factor away, but they're still on their path. And if you talk to the companies here, they would say, but now we're building a bigger device so we can do better. So let's await this. Yeah. So I now have those 4 extremes: laser fusion, tokamak fusion, something in between, and something using electric fields or the fusion fission hybrid. Yeah. Let's turn back to where we started, smarter than ITER. Can't we improve on ITER itself, on the tokamak concept itself? Because why do we want to be smarter than ITER? Simply because ITER is getting a complicated device, which is very expensive and very big. So you could say, if there would be a way to make a tokamak smaller, it's much more acceptable. It will become smaller, then cheaper, and maybe development goes faster. Now, on making it smaller, I think there are 2 options. Yeah. Well, there are not 2 options. There is a reason why it is big. First, the fusion power scales with the pressure squared times the volume. Yeah. So the pressure squared is the number of particles that can collide with each other. And the more particles you have, so if the volume is larger, you have more particles. So it's logical that you have this. Now, the pressure in a reactor, if you have a tokamak, should be balanced by the magnetic pressure. The kinetic pressure and the magnetic pressure, they should balance. And the magnetic pressure goes with the magnetic pressure goes with the magnetic field squared, so this should go with the magnetic field to the power 4, just like was introduced to you by Susie Speller in the previous talk. That's why we need high magnetic fields, yeah, because of this strong magnetic field dependence. Since we want to, a reactor only works when the fusion power is bigger than the fusion loss. The loss goes with the area. Yeah, because you heat up the plasma and only by the fusion of power through the area, you lose the power. And that is why a tokamak is a large machine by principle, because the ratio between fusion power and fusion loss scales with the volume over area, and volume over area is size of the machine. This goes to the size to the power 3 and this size to the power 2. So this ratio increases when you make it bigger. That is why we end up with bigger machines. But if we could also make the magnetic field bigger, then we could reduce the volume. So there are 2 ways if you want to have this ratio positive: make larger machines or make larger magnetic fields. And I think this is the big new development in tokamak line of the last 5 years, whereas ITER has magnetic fields that cannot go beyond 15 Tesla. Now with the REPCO superconductor coils, we could go to maybe 25 Tesla or so. And then you see you could reduce the volume at least by a factor of 2 or even more than that. And this is the big startup called Commonwealth Fusion. They're building the tokamak called Spark now. It's an MIT startup and it's funded heavily, for instance, by Bill Gates, but I think in total they already received several billions of dollars on funding, and they succeeded in sorry, and they succeeded in building these big superconducting coils now. And I think next year they hope to put their reactor Spark into operation, which should be going to net positive energy production with a machine which is, I think, a factor of 2 and all dimensions smaller than ITER. So the volume is a factor of 8 smaller. So it would really be a big success and a big step forward if this would indeed work. But of course, if you make it smaller with the same power, you might have other issues like power load in the machine, forces on the magnets, etc. So let's see how this goes by. Then my one but last slide, closely related to the tokamak, of course, we also have the stellarator. I guess it must have been introduced somewhere today, but the big advantage of the stellarator compared to the tokamak is that it is steady state. And there's not so easy that you lose your confinement completely. So from the principle itself, I think a stellarator is the better version of a tokamak, but it simply has not been researched that much as a tokamak. That's why the tokamak line is still leading the competition. But from the concept itself, I think there are many big advantages to the stellarator. And it looks much more pretty, isn't it? Yeah. So let's answer the question, can we be smarter than ITER? I hope to give you some insights how we could see all the different concepts. I think there are ways to make a tokamak or a fusion reactor much smarter than ITER. We could stick to the tokamak line and there are ways to make it smaller. We could go to a tokamak plus line. I call this the stellarator. Yeah. Or there are other concepts which we cannot immediately discard, although they are lagging way behind to what has been reached in a fusion reactor. But however, whatever the solution will be, I'm also convinced that a fusion reactor never will be small, simply because the tritium, in my opinion, is the fuel to go for, and all the tritium handling and the fact that it's a nuclear facility makes fusion big. Yeah. Then a final word in the present situation where there are many new startups, some of which I really think will never work. Still, I think it might be useful to test those and see what we can learn from that. Having parallel developments will simply speed up the fusion development, and that's a good way. So let's hope that in 10 years from now, this is the situation. The first fusion power plant in a green environment.
Oh,
Thanks
yes.
for your attention. Let me know if there are further questions.
Thank you very much for this amazing presentation. It was just a great overview of all the issues that are being tackling at this moment with the fusion companies and all this myriad of different concepts that are being weighted at the moment. So I think the comments are epic presentation, amazing presentation. Hope to get some.
Okay, that's good to hear. Let's see if I can read this.
Yeah, it's in the chat.
Okay.
In the meantime, while we wait maybe for a question, you mentioned at the very end of the presentation about the parallel, that it's the road to go is to explore parallel concepts. So would you foresee a race in the upcoming years, or how do you see the fusion environment while we explore
That's a
this?
good question. So first, there are two different races going on. Yeah, there are private companies who wants to be the one saying, "Hey, our concept is best," and moreover, also the governments and public, it has triggered a kind of a race. Yeah, there are the big players say the US has increased their fusion budget by a factor of 2, I think. Germany has recently announced they will spend $1 billion in the next 5 years on fusion, which is also a factor 2 more than before. The UK has come up with their own program, spending much more money in fusion. And then China is the one who probably has made the biggest increase. I don't know about numbers. I only read that they are outweighing any increase in budget that the US has done. So they spend most of it, simply because all these governments say, hey, we want to be the first one to have a fusion power plant in there. And for the fusion community, And I think the students in here, they are part of that. That's very good. It means more money flows into the system. We need more people in the system, because if twice or three times as much money flows in the system, we need 2 or 3 times larger workforce. And so there are plenty of opportunities. And if I may, if you allow me to make some advertisement, if you're really interested, come to Eindhoven, where we have a Fusion Master program. We need you.
That's a very good advertisement, and I have to say also that actually this lecture is part of the topics discussed in the master, isn't it?
Yes, of course.
Yes. Yeah. So yes,
but more details will be in there.
Of course. So yeah, so I think the students can contact you or contact Fusion about this or the Fusion group with Eindhoven. So yeah, we're looking forward to that. Thank you very much, Roger, for the presentation. If you want to stay for the picture, you're very welcome.
Okay.
We're gonna make the second try for our group picture today.